Have you ever wondered what makes the universe tick? I mean, really tick. We're talking about the deep, fundamental rules that control everything. From a planet spinning in its orbit to, an apple falling from a tree. We're going to dive into that rule book right now. Let's do it.
Okay, so what's the connection? Well, it's pretty amazing, actually. All of them, they're all playing by the exact same set of rules, the same unbreakable physical laws. And stick with me, because by the end of this, you're not just going to know the answer, you're going to get why it's so incredibly cool. Okay, but look, before we can just jump in and read this cosmic rule book, we got to learn the language, right? And that language, well, it all starts with the basics, the vocabulary of motion.
All right, first up, speed. Super simple, right? This is the one we all get. It's just how fast you're going. That's it. How much ground you cover in a certain amount of time. Like miles per hour, or if you want to sound like a physicist, meters per second.
Now let's level this up a bit. We've got speed, but in physics, we need something more precise. That's where velocity comes in. All it is speed plus direction. See, in the rulebook of the universe, knowing where you're headed is just as important as how fast you're moving. So saying you're going 10 meters per second, that's your speed. But saying you're going 10 meters per second due east, now that's a velocity. And trust me, that little difference is a huge deal.
Okay, and this leads us to one of the biggest ideas in all of physics. Seriously, acceleration. And I know what you're thinking. That's just flooring it in your car, right? Hitting the gas. But it's so much more than that. Remember how velocity includes direction? Well, any change in velocity is acceleration. So yes, speeding up, that's acceleration. Hitting the brakes and slowing down, also acceleration. And get this, even taking a turn at a perfectly constant speed, that's still acceleration. Why? Because your direction is changing. Mind-blowing, right?
All right, one last bit of language we've got to nail down before we get to the good stuff. Mass versus weight. People mix these up all the time. Your mass is just the amount of stuff you're made of. It never, ever changes no matter where you go in the universe. Your weight? That's totally different. That's the force of gravity yanking on your mass. So think about it. On the moon, your mass, the amount of you, is exactly the same. But because the moon's gravity is way weaker, you'd weigh only about a sixth of what you do here on Earth. Okay, so we've got the language down. We're ready. Now it's time to meet the guy who basically translated this cosmic rulebook for all of humanity. I'm talking, of course, about the legend himself, Sir Isaac Newton. And you have to understand, what he figured out was a total game changer. I mean, revolutionary. Before Newton, pretty much everyone thought there were two sets of rules. One for us down here on Earth, and a completely different, perfect set of rules for the heavens. Newton's big aha moment was realizing, nope, it's all the same. The very same force that pulls an apple off a tree is the exact same force that holds the moon in its orbit around the Earth. One universe, one set of rules for everything. And here they are, the core of the rulebook, his 3 laws of motion. First law is all about inertia. Basically, things just want to keep doing what they're already doing. If it's moving, it's going to stay moving, unless something pushes or pulls on it. The second law? That's the famous F equals ma. It's the recipe that tells you exactly how much force you need to change something's motion. And the third law is my favorite. For every action, there's an equal and opposite reaction. You push a wall, that wall is pushing back on you with the exact same force. Always. Okay, pop quiz time. Let's see if you've been paying attention. A car slams on its brakes. A bike whips around a corner. Jupiter's moon is just doing its thing, orbiting the planet. In all 3 of those cases, is there a net force at work? Think about what we said about acceleration. Did you get it? The answer is absolutely yes, for all of them. The car is decelerating, that's a change in velocity. The bike is changing direction, that's a change in velocity. And the moon? It's constantly changing its direction as it swings around in its orbit. All of those are acceleration. And Newton's first law tells us you can't have acceleration without a net force, period. Now, Newton's laws are amazing, right? But they actually hint at something even deeper, an even more fundamental layer of how the universe is put together. We're talking about the conservation laws. And these aren't just rules. These are more like cosmic commandments. As far as we know, they are absolutely 100% unbreakable. First up, we've got the conservation of momentum. What's momentum? Just think of it as oomph, an object's quantity of motion, its mass times its velocity. And this law is simple. The total amount of momentum in a system can't change. It can get passed around, like a cue ball smacking into the 8-ball, but the total amount of oomph before and after the collision, it stays exactly the same. It has to.
And there's a spinning version of this too called conservation of angular momentum. This explains the classic ice skater trick. You've seen this, right? When a skater is spinning and she pulls her arms in, she suddenly speeds up like crazy. Why? It's not magic. By pulling her arms in, she's making herself smaller, so to keep her total angular momentum the same, her spin speed has to increase. And this isn't just for skaters. This same unbreakable law is why the Earth keeps spinning and why it stays locked in its orbit around the sun. And now, for the big one. Probably the most famous scientific law of all time, the conservation of energy. I like to think of energy as the universe's currency. It's what makes literally everything happen. And the law is so simple, but it's incredibly profound. You can't make energy from nothing, and you can't destroy it. All you can do is change it from one form into another.
So what forms does this cosmic currency take? Well, at the most basic level, you've got 3 main types. There's kinetic energy, that's the energy of motion. Potential energy, that's stored up energy, like a roller coaster at the top of a hill. And radiative energy, energy carried by light. And get this, every single thing that happens, anywhere in the universe, a star going supernova, a chemical reaction, even a thought firing in your brain, it's all just energy changing from one of these forms to another. So there we have it. Our complete rulebook is assembled. We have Newton's laws. We have the conservation laws. Now for the fun part. Let's use this rulebook to crack some of the universe's most famous mysteries. Okay, first mystery. You've all seen it, right? Astronauts just floating around inside the International Space Station, totally weightless. And the obvious answer is, well, there's no gravity in space. But is that right? Is there really no gravity up there?
Nope, not even close. In fact, where the space station orbits, Earth's gravity is still about 90% as strong as it is right here on the surface. So what's going on? The real reason they feel weightless is because they are constantly falling. They, and the space station around them, are in a perpetual state of freefall. They're just moving sideways so fast that as they fall down, the Earth curves away from them at the exact same rate. They're basically missing the ground, forever.
All right, next up, the tides. We all know the moon has something to do with it, but how? How can that little rock in the sky pull on our gigantic oceans? Well, the secret isn't just the moon's gravity itself, it's the difference in its gravity across the Earth. Think about it. The moon pulls a little bit harder on the side of the Earth that's closer to it, and it pulls a little bit weaker on the side that's farther away. This difference creates a stretching force. It literally stretches our entire planet. And because the oceans are liquid, they bulge out on both the near side and the far side, giving us 2 high tides at any given time. Okay, for our last mystery, let's go way back to Galileo. You've probably heard this one. If you get rid of air resistance, a heavy bowling ball and a light feather will hit the ground at the exact same time. But that just feels wrong, right? I mean, gravity has to be pulling harder on the heavy ball, right? And you'd be right, gravity does pull harder on the heavier object. But, and here's the genius part, that heavier object also has more mass. And more mass means more inertia. It's harder to get it to change its motion. And the beautiful, elegant secret of our universe is that those 2 things, the stronger gravitational pull and the greater resistance to moving, they cancel each other out perfectly every single time. It's just a stunning example of how perfectly these rules fit together. And that kind of leaves us with one last big idea to chew on. We've just seen how a few surprisingly simple rules can explain everything from orbiting planets to ocean tides, the whole grand dance of the cosmos. So it really makes you wonder, doesn't it? What other super complex things out there, maybe in biology or in our societies, or even in our own minds, what if they're also built on a foundation of simple, elegant rules, just waiting for us to figure them out?